You're listening to the sounds of space right now. These are measurements of waves in our magnetic field taken by the Van Allen probes, which are in space, in orbit around the Earth. I'm going to ask you some questions to begin with. So, who here, by a show of hands, knew that space has radiation in it? Oh, fantastic, you've all read my talk title. I knew it because that's what my PhD is in. Now, who knew that space is not a complete void? Yeah, this is great. My job's done and I can go home. It's not complete void compared to the air that we breathe. It's empty. But there are particles there. There are a few of them. The solar wind is an example. It flows from the sun, particles with enough energy to leave the gravity of the sun's surface are ejected into space. And they travel at speeds of about 400 kilometers per second. So really fast particles with lots of energy. However, there are so few of these particles that when I blow in the air, that is 1,000 times stronger than the solar wind. Now, my final question is, who here knew that there is weather in space? Yeah, this is great. There is weather in space. These conditions are variable. These particles can vary in energy and location. And this weather can cause big issues for our technologies in space. We are so reliant on infrastructure like satellites nowadays. And it's actually on the UK National Risk Assessment. This is data from the 2015 risk assessment done by the UK government. And we can see lots of different risks to the UK on these panels. And each risk has a score for impact, and it has a likelihood of happening as well. And we can see that pandemic influenza is the biggest risk to UK because it has a high impact and it's very likely to happen. But severe space weather is actually really high on this risk register as well. One of the effects of space weather is the aurora, this beautiful light show. And this is the Aurora Australis, as seen from the International Space Station. It's these energetic particles which rain down into our atmosphere and create these lights. But not all of the effects are quite so beautiful as this. This is a test done to spacecraft electronics by the European Space Agency. And they fired radiation at their circuits, and they became so hot that the components melted, and you can even see that. That's tiny, minuscule. And as technology has progressed, our circuit boards, as we saw in the last talk, are getting smaller and smaller, and they need less and less current. And this means that radiation has a higher and higher impact. What can also happen is a general charging of a spacecraft. Radiation comes around and gathers around it until there's a big discharge of electricity, like static. And this can also damage our spacecraft. But it's a risk to astronaut health as well. We all know that we are susceptible to radiation in our bodies. So we need to be aware of this risk for human spaceflight. But it's not just astronauts who are susceptible to this radiation from space. If you're going over the pole at a high altitude in an aircraft and there's a big radiation storm, you can be exposed to this radiation from space as well. There are other effects, such as communication blackouts, and GPS also gets disrupted. If you're wandering around on Google Maps, you won't notice it, But if you're trying to drill oil at very high precision, then it matters. And what can also happen are currents flow through the Earth's crust. And this can heat up our power grids and cause blackouts for hours at a time. But the topic of today, for me, is radiation and how it matters for spaceflight. But what is radiation? Radiation is light, an electromagnetic wave, or it can be a particle, an electron or a proton or an ion. But the only type of radiation that we need to be really worried about is ionizing radiation. Now, this is radiation with enough energy to impart its own energy onto matter, and it excites electrons out of those molecules. We're gonna switch. There we go. We experience radiation every day. It's in the air that we breathe, in the radon. If you're lucky enough to have a granite worktop in your kitchen, you get a higher dose of radiation than everyone else. And if you eat a lot of bananas in your kitchen, you also get a higher dose of radiation. But everyone, every day, experiences radiation from space. And this is the way of cosmic radiation. So, in supernova explosions in space, these particles are accelerated extremely fast, and they travel from the star or from other galaxies even, and come through our atmosphere. And at our upper atmosphere, they interact with the molecules. And this creates a cascade of chemical interactions which rain down to the surface of the Earth. And these particles, which result from these interactions, are still very energetic. So that's what we feel on the ground. And we've known about this radiation for a very long time because we can feel it. So when the US sent the first satellite into space, Explorer 1, it had a Geiger counter on board, so it could count the amount of radiation directly from space. But they had an issue. And that was that no one put a tape recorder on board. So the only time that they could get this data was if Explorer 1 was flying over your head and you had a receiver on the ground and you could take the measurements. And sometimes they would get a normal count of radiation. Sometimes it was an extremely high count, and sometimes, mysteriously, there were no counts at all. And unfortunately, Explorer 2 did not make it to space, but Explorer 3 did, and they put a tape recorder on board so they could record an entire orbit of radiation. And it was James Van Allen who mapped out this radiation and realized that below 1,100 kilometers, you had a normal radiation count. Above this was where you either had very high counts or no counts at all. And they realized it wasn't that there were no counts, it was that there were so many counts that their instrument has completely saturated. And this is the first figure in scientific literature of the radiation belts, and this really excites me. It's now called the Van Allen belts, and the circle on the left is the Earth, and the shaded regions are the regions where they mapped high levels of radiation. In a more public-friendly picture, they drew them as shells around the Earth. There's an inner belt close to Earth, and there's an outer belt. And there's a mysterious slot region in between them as well. But how can radiation become trapped in the first place? Well, the answer to that is magnetic fields. So we've all done this experiment. We have a dipolar magnet, put it on a piece of paper with iron filings, and they line up to that magnetic field. You can see it. And this is similar to particles which are charged. They interact with that magnetic field. And the Earth is a giant dipolar magnet. There are there's iron molten in our core, which swishes and swirls, and that creates a dynamo effect and generates this huge magnetic field, and that can trap particles. Before Van Allen and his team discovered the belts, it was actually understood that these particles interacted with our magnetic field. The first person was Christian Birkeland, who took a magnetic ball, which was very similar to the Earth's magnetic field, and he shot electrons at it. And he saw it glow, just like the aurora. He created an aurora in his lab. But he did not quite understand the mathematics of it. So it was his supervisor, I wish my supervisor would do this for me, who figured out the particles' motion in this magnetic field. So I'm going to show you an animation. In a steady magnetic field, which is shown by the blue lines, a particle spirals around in a circular motion. But if this magnetic field gets stronger, like where the lines converge, the particle is reflected from that region of high field strength, and it comes back at you. He also realized that if you have two regions of a strong magnetic field, you can trap a particle because they bounce between these two regions of high field strength. It was Carl Stromer who then looked at relativistic particles in a dipolar field, because if you have a degree in physics, you know there are no magnetic monopoles. At least we've not found any yet. So, it's very similar to a magnetic bottle. At the poles of the Earth, our magnetic field gets stronger, and the particles bounce back and forth. But as well as this motion, they drift around the Earth at the same time, almost like they're in orbit, but it's like a magnetic orbit. And this creates that shell of radiation which Van Allen observed. Now, I like this man, Nicholas Christopoulos. He was an elevator engineer from Athens, and he had a strong interest in magnetic fields and particles. And he discovered strong beam focusing technique, which is now used in particle collider experiments. And he wrote to scientists in the US to tell them of his discovery, but it was never published, and the scientific community were none the wiser until someone else independently discovered this effect. And he did get the recognition in the end. But because of this, he was invited to the US to be a scientist. And something he was really interested in was an Astron thermonuclear device. What is this, you ask? Because I hadn't heard of it. It's where you have one of these magnetic bottles with a strong piece of field at either end, and you trap your plasma, so your electrons and your protons, in this bottle. And it gets heated until nuclear fusion can occur. And the way that he wanted to test this was with the Earth's magnetic field, our natural magnetic bottle, and with a nuclear bomb. A nuclear bomb creates this very high energy, this radiation, and if you set it off in Earth's magnetic field, far away from Earth, then these particles can become trapped. And this experiment was improved, and it was planned to be taken out in 1958. But in the meantime, they discovered the natural radiation belts, which was great for the science because they knew it could happen, that these particles can become trapped. So they went ahead with their experiment. And something I found interesting in my research of this was that James Van Allen himself, the discoverer of the radiation belts, was involved in this project. And he wrote to the US government to tell them that this experiment should not be a secret, because in the eyes of the world, the US would be Sputniked by the Soviets. So the next year, they made this test public. They set the nuclear bomb off and created a detectable radiation belt artificially. And they expected that it would last maybe a few days, but it lasted a few weeks. So this radiation lasts longer than they thought. And Nicholas actually had another theory, and that was that if you fill space near Earth with enough radiation, it would damage the electronics in a nuclear warhead, so it wouldn't be able to detonate. In the next few years, the US and the USSR filled space with lots of radiation during the Cold War. Now, this is Starfish Prime nuclear test, and this was done along above the Pacific. And the flash in the right image is of that nuclear bomb from Honolulu. But on the left, more interestingly for me, is the aurora above Hawaii. When this bomb exploded, there were so many particles it went into the atmosphere and created the aurora. And apparently, there were many hotels in Hawaii who held rainbow bomb parties on their roofs to see this spectacular light show. But it wasn't all fun and games. There were numerous satellites which were completely lost and irrecoverable because of the radiation damage to their electronics. And the artificial radiation belt that they created lasted so long that years after the tests, they still had concerns for the astronauts' health and safety from this new radiation belt that they created. But by the time that the Apollo missions came along, it had decayed enough, and the US decided that it was a risk that they will take. But back to the science. So we know that there's an inner belt and an outer belt, but we don't really know where they come from. Well, the inner belt is mostly made of protons. And this is created in the cosmic ray albedo neutron decay, which is quite a mouthful. And in the same shower, that raining down of particles into the atmosphere from that cosmic ray, you can get one neutron which goes up, not down, and it escapes into space. And because it's not a charged particle, it doesn't see our magnetic field, so it can fly freely until it decays, because neutrons are very unstable. And it creates an electron, a proton, and an antineutrino. And the proton gets most of the energy, and it spirals around the magnetic field and becomes trapped, creating the inner belt. But the electrons, which we can see by the warm colors in this image, are showing where we have high levels of radiation. The electrons are much more dynamic than this. They're not created in the same way. And we see sometimes the belts get really small, sometimes they expand really big. And the structures are changing constantly. And this is what I, as a scientist, am trying to understand. We're trying to forecast these changes. And to understand them, we need to look at the sun. So the sun has a very strong magnetic field, but it's not a dipole like Earth's. It gets all twisted on the surface, and like an elastic band, it gets so twisted that eventually it snaps. What's known to me as a magnetic explosion, but to everyone else, it's a coronal mass ejection, or CME. So these magnetic explosions snap, and they take all of that trapped particles and eject it into space. And then all of these particles fly towards us at Earth. But we have a magnetic field to protect us. This is great. It's dipolar, but it becomes contorted by the solar wind, as you can see. And as the coronal mass ejection reaches Earth, it imparts its energy. It loads all this energy into our magnetic field until eventually our magnetic field becomes so stressed that we get a geomagnetic storm. Now, this is another magnetic explosion where there's a reconfiguration of our magnetic field. It'll happen now. And when this happens, solar wind particles are allowed into our magnetic field, and they are energized. And they come closer to the Earth by diffusion, and they become relativistic. And that's how we get the electrons in the radiation belts. But I still haven't explained this gap in between the belts, this is the region called the slot region, where there's no radiation. And we have to look at wave-particle interaction. So much like the magnetic field interacts with the electrons and protons, electromagnetic waves can do the same. So this is one example of one of these waves. You have a lightning storm at the ground, and an electromagnetic wave comes up, and it's guided by our magnetic field until it reaches the radiation belts in space, and it interacts with the particles there. And that changes their trajectory so that they no longer see that strong magnetic field at the pole, and they can interact with our atmosphere. And then we lose them. If there are enough of these wave-particle interactions, then we get a gap in our radiation belt where the particles are drained. In the 90s, our understanding of the radiation belts were changed. SAMPEX was a mission which was launched, and they discovered that the solar wind particles coming in during a geomagnetic storm were not energized enough to create the radiation belts. So we had to use wave-particle interactions to explain this as well. Now, we're looking at a magnetic field constant in the background, and there are two particles spiraling around it, and there's a wave that comes in. And you can see it gaining energy. It's getting faster and faster. So this wave is giving that particle energy until it becomes radiation. And the Van Allen probes, my personal favorite mission, was launched in 2012, and they found evidence for these wave-particle interactions. And they measured these waves. Now, there are a whole zoo of waves in our magnetic field. And whilst they're not sound like we know sound, they have a frequency. So we can play this frequency and listen to it. And for this part, I'm going to need a volunteer who has a good singing voice. You still want to sing for? Yeah, you can do it. We can do it together. Okay. You speak down the microphone. Is it on?
Yep.
Okay. So, one of the waves is called plasmaspheric hiss. What do you think that sounds like? Yeah, I'll play it for you and we'll see if you got it right. Pretty good, right? Did a good job. It's a hiss sound, but it's kind of undulating. Does it sound like the sea? Yeah, it's like waves in the sea. Okay. The next wave that I want you to make the sound of is called a whistler mode wave. Can you whistle? That's perfect. Let me play it. That was really good. Well done. This sounds like you're in a battle in space, right? That's the last wave. That's the chorus wave. What do you think a chorus wave sounds like? La. Oh. You have a beautiful voice. Can we thank him? We can hear that wave in the background, the chorus wave. It's like a... It's actually named after the morning chorus, the sound of the birds in the morning. That's them all together. So the Van Allen probes also made another discovery, and that was a third radiation belt. So we know that we accelerate electrons and we lose them into the atmosphere. But occasionally, the rate that we lose them is not enough to catch up with the acceleration. And every now and then we get a third transient belt. But there's so much about the radiation belts that we still don't understand. And that's what I'm working on. But the radiation belts themselves are a risk to humans, but a small risk. And today's talk, well, not the talk, but the day, is about the Apollo missions. Each Apollo astronaut had a radiation monitor on their body because, yes, they were worried about the radiation belts and the dosage. And when the astronauts returned to Earth, they detected levels from this instrument of about a chest X-ray, which isn't a big danger to us. But the radiation belts are not the only radiation in space. We're looking at the sun right now. And we're going to look at some events called the 2003 Halloween storms. And it started by a solar storm. And then it created a geomagnetic storm. And there was a radiation storm. So we're looking at the sun through a filter, which is why it looks green. We're just seeing one wavelength of light. And you can see these flashes as they go off. And those are solar flares. And the solar flares are putting energy into the magnetic field of the sun. And eventually, so much energy is put into them that there are these explosions of magnetic field, these coronal mass ejections. Now, I'm not a solar physicist, and I can just see some small explosions on the surface of the sun. So I like to look at a different view. I'll just pause that. This is a coronagraph. So we have the same green picture of the sun in the center for scale, and the round disk is essentially an artificial eclipse. We're blocking out the light from the sun. And all of the blue is the sun's light scattering off plasma. So the more plasma that we have, the more electrons and protons, the brighter it appears. And we can see these explosions blasting into space. You can see them. And there's a really big one that's going to come, and it appears as a halo. Now, I'm going to play this again because I enjoyed the video. You don't have to worry about the ones which look like loops so much. When you have to worry is when it looks like a halo from the whole sun, because that's coming directly at you. Now, we saw this whiteout effect. We saw the white flashes. Does anyone know what those are? What do you think they are? Exactly. They're radiation. They're these energetic particles which are imparting their energy on that camera. Well done. When the astronauts were on the moon, when they closed their eyes, they saw lights like this in their vision. And that's the radiation that they saw hitting their retina. And the sun is a huge particle accelerator. They create this huge amount of radiation during these storms. And it's this radiation that was the biggest risk to the astronauts on the Apollo missions. So what the astronauts were doing that was so dangerous was leaving our magnetic field. These are little particles in that coronal mass ejection that's being fired at the Earth, and we can see they don't reach us on the Earth. They're guided away from our magnetic field. So our magnetic field can trap and create some radiation, but that radiation is very easy to avoid. We just don't go through it, or go through it very quickly, which is what the Apollo missions did. You leave the magnetic field and you're exposed to this radiation. And we work on forecasting when these particle events will occur, but it's very difficult. And a lot of people say that the Apollo missions were extremely lucky. Now, this is a picture from Apollo 16, and not long after they were on the moon, there was one of these events. If they'd been on the moon at the time, They would have suffered acute radiation sickness. They would have had to immediately leave, come back to Earth to receive medical care, which could have been life-saving if they'd made it back at all. But there are ways that we can protect ourselves. We can shield our spacecraft, and we can go underground on the moon, which is probably what we'll do if we ever have a moon base. But what I think is most important is understanding how to forecast these events, looking at the sun, looking at the interactions of this space weather. Thank you.